Okay, let's dive right in. Today in this explainer, we're completely demystifying bit manipulation. You know, that hacker Swiss Army knife for technical interviews. If you've ever stared at a flawlessly optimized algorithm and thought, wait, how on earth did they come up with that? Well, chances are they were playing around directly with bits. We're going to take these concepts, which, honestly, can look like sheer magic, and break them down into practical, reliable tools for your coding arsenal.
And this right here perfectly captures the stakes we're dealing with. You've got your standard operations, right? Looping through arrays, doing math, and taking up linear ON time. Sure, it gets the job done, but it's the slow way. On the flip side, bit manipulation lets you solve complex array and math problems instantly, like literally in O of 1 time. This isn't just some minor tweak. This is the difference between a pretty good solution and the exact mind-blowing solution your interviewer is desperately hoping to see.
So here's our roadmap for today. We'll hit the magic of bits, the core binary toolkit, XOR for finding the duplicate, clearing bits to count, checking powers of 2, and finally, some final interview takeaways.
Section 1. The magic of bits. How computers see numbers. We're completely bypassing base 10 today to operate right on the raw binary.
Moving to Section 2, the core binary toolkit and its operators.
Think of this as your fundamental binary cheat sheet. We've got AND, OR, XOR, NOT, and your left and right shifts. We use these specific operators to manipulate bits directly, which means we bypass standard math entirely. So instead of dividing by 2, you just shift a bit to the right. Instead of adding, maybe you use an OR operator. Mastering these symbols is basically your VIP pass to writing that ultra-efficient O of 1 code.
Section 3, XOR, finding the duplicate, or as I like to call it, the power of canceling out.
Okay, so we're going to explain the concept first, and then look at a real-life problem to understand it more. Here's the core theoretical trick. XOR logic dictates that if you XOR any number by itself, it essentially self-destructs right into 0. It doesn't matter if the number is 5, 50, or 5 million. If the bits are identical, XORing them against each other wipes them out completely. You are left with 0.
So how do we actually use this? Let's take that concept and apply it to a classic interview problem. Imagine you have a massive array. Inside this array, every single number appears exactly twice, as a pair. But there is one unique number hiding in there that appears only once. How do you find that single non-duplicate element efficiently? If you throw a hash map at it, you're eating up O of n extra space. If you use nested loops, you're burning O of n squared time. Honestly, both of those are going to get a frown from your interviewer.
But here is the incredibly elegant O1 space solution. Step 1, just iterate through the array once. Step 2, keep a running XOR of all the elements together. Step 3, because order literally doesn't matter with XOR, every single pair of duplicate numbers will eventually XOR against each other. And remember our rule? They cancel each other out to 0. And a 0 XORed with any number is just that number. So by the end of the loop, all the pairs have vanished into thin air, leaving only the unique number standing. It feels like pure magic, but it's 100% grounded in logic.
Section 4, clearing bits to count, manipulating the lowest set bit. Let's look at the concept first again. Here is the raw trick. The formula is x and x minus 1. If you take any binary number, subtract 1 from it, and run a bitwise AND operation between the two, it magically erases the rightmost 1 in that binary sequence. It just flips it straight to a 0. We call this clearing the lowest set bit. Take a second to lock that formula into your brain, because its application is incredibly common.
And here's exactly how an interviewer is going to test you on it in real life. They'll ask something like, how do you count all the set bits, meaning all the ones, in a number efficiently? Now, the intuitive brute force approach is to loop through every single bit one by one, shifting and checking if it's a 1 or a 0. But think about it. If you have a 64-bit number and only 2 of those bits are actually 1s, checking all those zeros is way too slow and completely unnecessary.
Instead, we bring in our clearing trick. Step 1, initialize a count at 0. Step 2, set up a while loop that runs as long as x is not 0, and inside, execute x equals x and x minus 1. Step 3, increment your count every time the loop runs. Why is this so brilliant? Because you're instantly jumping from set bit to set bit, clearing them out one at a time. If a massive number has only 3 ones in it, your loop only runs exactly 3 times. It skips all the zeros entirely. That right there is the definition of a truly optimized algorithm.
Section 5. Checking powers of 2. The classic interview filter.
Building on our last concept, let's look at a really cool variation. Instead of clearing the bit, what if we want to isolate it? The formula x and negative x lets us isolate that lowest set bit completely. While x and x minus 1 turn the lowest 1 to a 0, x and negative x literally zeroes out absolutely everything else except that lowest 1.
So here's the real-world application. How do we use these clearing and isolating concepts to solve the absolute classic, is this a power of 2 question? The prompt is simple. Given an integer, verify if it's a power of 2. But here's the catch. You generally need to do this without using any loops and without using any division operators.
And here is the ultra-clean solution. Return true if x is greater than 0 and x minus 1 exactly equals 0. Let's really think about the logic here. A power of 2, like 2, 4, 8, 16, in binary always has exactly one bit set to 1. Everything else is a 0. Like 4 is just 100 in binary. Since it only has exactly one bit set to 1, if we use our trick to clear its lowest set bit, the entire number has to become exactly 0. If it doesn't become 0, well, it had more than one 1 and therefore simply cannot be a power of 2. It's such an incredibly satisfying piece of logic.
Section 6. Final interview takeaways, your rapid-fire toolkit.
All right, here are your rapid-fire solutions to keep in your back pocket. Number 1, to check if a specific bit at index I is a 1 or 0, shift x to the right by I and AND it with 1. Number 2, to set a specific bit to 1, use x or 1 shifted left by I. Number 3, to clear that specific bit back to 0, use x and the not of 1 shifted left by I. And finally, number 4, which is honestly a brilliant party trick, you can actually swap two variables a and b without ever using a temporary placeholder variable just by chaining XORs. It's a XOR equals b, b XOR equals a XOR equals b. Boom, swapped.
Now look, I know that's a ton of syntax to absorb all at once. So let's ground ourselves with this core advice straight from the source material. Don't memorize all tricks at once. Learn XOR and the power of 2 check first. They appear most frequently. It is so much better to deeply understand the logic behind why XOR cancels out duplicates, or exactly why clearing the lowest set bit identifies a power of 2, than it is to just blindly memorize syntax. Master the concepts we just walked through, and the syntax will naturally follow.
And that completely wraps up our explainer today. We've taken binary from basic 1s and 0s all the way up to O of 1 algorithms that can breeze through the most rigorous technical interviews. So I'll leave you with this. Which of these O of 1 magic tricks are you going to add to your algorithm strategy next? Until next time, keep exploring and keep optimizing.